Hello everybody and welcome to this walkthrough of the Senior Kangaroo Maths Challenge. So the Senior Kangaroo is coming up later this month on the 30th of November. From what I remember of the Senior Kangaroo, I did it when I was in school a few years ago now. What happens is you do the maths challenge and then you receive your results and they tell you, oh, you've done quite well, and then all of a sudden they put you into this Senior Kangaroo in the next 1 or 2 weeks. And you just go, oh, I've never heard of this, I have no idea what I'm doing. And actually there are very few resources online that actually help students through these sorts of problems. So what I'm aiming to do today is what I've done is I've got a PDF with one of the questions on each page, and I'm simply going to go through and, as if I was attempting the exam myself, I'm going to have a go at answering these. Now this is the 2017 paper, so it's the most recent one as I'm recording. And we'll just see how it goes. So as a bit of an introduction to this competition, the way it works is they take the highest scoring sort of I think it's about 6,500 students from the maths challenge. The top few hundred of those go to do the Maths Olympiad, the BMO one, but the rest go to this, are entered for this Senior Kangaroo. And this is basically a slightly harder version of the Senior Maths Challenge, but it's not multiple choice, although I suppose technically it is. All answers will be between 000 to 999, so all of them are going to be in the form, well, it'll be like 013 if the answer is 13, or 312, like this. But it's not really multiple choice in that there's no real advantage to just guessing. There are 20 questions, and 5 marks are awarded for each correct answer. No penalty for incorrect answers. Although it does stress, think, don't guess, which is wise advice when there are 1,000 different options for each question. It's worth saying as well that these questions are quite difficult, so actually the standards, the grade boundaries are not that high. So for this particular paper I looked online, and the top 25% receive a merit, but the score for a merit needed was 40. And bearing in mind you get 5 marks for each question, that means essentially if in 1 hour you can get 8 questions correct, then you will actually get this merit. And so you're not actually expected to answer, all of these or even half of them correctly in this hour. You don't need to think in terms of 3 minutes per question. Rather, it would be better for you to focus on maybe 10 to 12 questions and really try and get them right. Make sure that you get them right. But yeah, so what I'm going to do is I'm just going to go through all the questions. I'm not sure how long it'll take. I don't think we'll get it done in an hour, although we can try. And I'll just go through and hopefully you'll get a bit of an insight into my thought process, how I'm going about the questions. You'll see that some questions take a long time. Some of them I'll spot very quickly. Sometimes I'll be fumbling around, not quite sure what to do. And hopefully it will just be helpful to see that thought process played out. But also, my plan is to actually get the right answer to at least most of these problems. And so you can also treat this video as a solutions video, as well as a walkthrough. So without further ado, I'll just have a drink and then we'll get started. Okay, so we're 4 minutes into recording, and so I'll mark when 1 hour passes, but let us begin. Okay, question 1. An integer is to be written in each circle of the network shown. So they've helpfully filled in 4 and 7 for us already. And the rule is that the sum of the numbers at the end of each line segment is the same. What is the total of all the integers? So we need to fill in the rest of this and find the sum of the integers. And the rule is that the sum of the numbers at the end of each line segment is the same. Each line segment. I can only imagine that they simply mean this. So this is each line segment, this is a line segment, and this is a line segment, and this is a line segment. So if I'm right about that, it's a little bit ambiguous, but this is probably what it means. Then if this is 4, and let's say we've got another one here, then these have to be the same, don't they? because we're saying the sum of this line segment's numbers and this line segment's numbers has to be the same. Okay, so we roughly get what's going on. So let's say this is x. Then this has to be x because the sum of each line segment has to be 4 plus x. But that means this has to be 4 for this to be 4 plus x. So we can kind of go around like this for x. So actually, x is 7. So the sum of each line segment has to be 11. Okay. So now I think we can just fill in our entire grid with 4s and 7s. So 4, 7. 7, 4, 7, 4, 7, 4, 7, 4, 7, 4, 7, 4, 7, 4, 4, 7, 4, 7, 4, 7. Okay, what is the sum total? So the sum is, how many 4s do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think we've got 12 of them. So 12 times 4. And I think by symmetry we're going to have 12 7s as well, although you could check that if you weren't sure. So that gives us 24, 48, and 12 7s, well that's just 84. If we add this up we get 132, so the answer to the first one is going to be 132. Okay, question 2. We've got 3 sportsmen, Primus, Secundus and Tertius, so 1, 2 and 3. On Saturday, Primus wins, Secundus is second, Tertius is third, fittingly. And so we record the result as 1, 2, 3, that makes sense. On Sunday, Primus starts the race in the lead, Secundus in second, and then it must be Tertius in third. And we're told Primus and Secundus change place 9 times. So if you imagine that, each of those 9 times, forgetting 3 for the moment, after they flip once, it's going to be like this. Maybe with 3 here, maybe with 3, maybe with 3 here, maybe with 3 here. Doesn't matter. But then when they swap again, so that's after 1 time. After they swap again, it's going to be 1, 2. Swap again, 2, 1, and so on and so on. And so actually, if they swap 9 times, that's the same as swapping once. So we know that 2, let's say 2 beats 1. Now, Secundus and Tertius to change place 10 times, that's the same as not changing at all. So actually 2 beats 3. And Primus and Tertius change place 11 times, that's the same as changing once. So actually 3 beats 1. And so the answer is, how will Sunday's result be recorded? Sunday's result will be recorded 2, 3, 1. Okay, question 3. All 3-digit positive integers whose digit sum is 5 are listed in ascending order. What is the median of this list? Okay. Well, I don't know of any other simple way to do this other than just listing them all. So, the smallest one I can think of, they have to be 3 digits. So the smallest one would be 104. And now we can consider permutations of this. So this comes from 5 is 1 plus 0 plus 4. So we could also consider 140, 401, and lastly 410. I'm going to actually write these smaller. I'm going to try and write them all exhaustively, but also put them in order at the same time. That's kind of what I'm aiming to do. 140, 401, and 410. That'll be the next one. But also, 5 is 1 plus 1 plus 3. So we get 113, which goes here, 131, and 311. But we could also write 5 as 1 plus 2 plus 2. So that gives us 122. 212 goes about here. 221, and that's it. We've also got 2 plus 0 plus 3, so that gives us 203, 302, and 320. Is that all of them? Oh, and obviously 500. 5 plus 0, so 500 goes here. Okay, so how many numbers have we got? I think this is all of them. We've got 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. Is that all? We have to be really careful here. Is this all of them? The reason I'm hesitating is we've got 14, it's asking us to find the median. So you would actually expect that to be an odd number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So maybe that means I've missed one out. Oh, so that should be 2, 2, 1. 2, 2, 1. Oh, sorry. This is why I've missed out 230, which should go here. 230. Okay. That seems more promising. So we've got 15 numbers, so the median, that's the middle number, is going to be the 8th number. The 8th smallest. So this is 1, 2, 3, 4, 5, 6, 7. So the 8th biggest number is going to be 2, 2, 1. Final answer. Okay, that was a bit of a mess. I hope that's right. Question 4. This looks like a bit of a nicer problem. We've got a regular hexagon here, and 6 triangles and 6 squares. What is the outer perimeter? Okay, so, well, we know that these are squares, and we know that the hexagon has side length 18, which means this is 18. So actually, we know around the perimeter this length is 18, so we've got perimeter is 6 times 18, because we've got 6 of these, and plus 6, let's say 6x, where x is the length of these. Now, these triangles look equilateral, but are they? Let's see. If you imagine in a hexagon, we can split this into 6 triangles. What are the angles in this whole thing? Well, 6 times 180, because we've got 6 triangles, each of whose angles add up to 360. But then, if we minus all of these angles in the centre, we end up with all of these angles left over. So if we divide that by 6, we get the interior angle, of this hexagon. So the interior angle of the hexagon is, well, 6 times 180 over 6 is just 180. And then we've got 360 divided by 6, which is 60. So we know that the interior angle of, that's the interior angle of the hexagon, is 120. So let's just draw out our key bit. So we've got the hexagon here, which has interior angle 120. We've got a square here, so right angle, square here, right angle, and then we're left with this triangle. And we know that this is a square and this is a square. So this is 18, this length, and this is 18, this length. And now what is this angle? Well, all of this adds up to 360. So we've got alpha plus 2 times 90 plus 120 equals 360. And so actually, well, 2 times 90 is 180. 180 plus 120 is 300. So we get alpha is 360 minus 300, which is 60 degrees. And these two sides are equal of this triangle, which means this is isosceles. And isosceles triangle with an angle of 60 degrees means that the triangle is equilateral. And that means that this third side must have length 18. So another way of saying that is x is 18. And so if we plug that back into our expression for the perimeter, we get 6 times 18 plus 6 times 18. And that is 12 times 18. And that is, if we work that out, 180 plus 36, that's 216. So our final answer is that the length of the perimeter is 216. Okay, question 5. The figure shows a quadrilateral with AD equals BC. Okay. Point E is the foot of the perpendicular. The length DE is 25, and these are the same. So let's just say that these are the same, like that. And we have to find the area of the quadrilateral. Now, the question is, what is DE doing? It forms a right angle here, but why have they put that in? It leads me to think, why don't we make this a rectangle? It's a pretty poor straight line, I'll try again. Make this a rectangle. Okay, and now we see that actually we've got, let's call that F. We've got DFEB, and this is a right angle. But then we've also got this as a right angle as well. And can you see that that means that this angle here, alpha, is the same as this angle here, alpha? Does that make sense? And we also know that these two lines are the same. And so what we end up with is this triangle here and this triangle here. They're similar because they both have a right angle and an alpha, so their angles are the same, but they also have a common length line because DA is the same length as DC. So actually these two triangles here, this triangle and this triangle, they are actually congruent. They have the same lengths. And so actually that means they have the same area. So we can forget about this and just consider this. Okay? So we don't need to find the area of the quadrilateral because we know it's equal to the area of that rectangle. So the only remaining question is, how long is DF? But we already know because these triangles were congruent. DF is equal to DE, which is 25. So, because these triangles are congruent, they have the same length sides. So the area of the quadrilateral is actually just the area of this square, which is 25 squared. And 25 squared is 625. Final answer. Brilliant. Okay, question 6. So we have all the numbers from 1 to 2017 on a board. We erase all of the integers that are a multiple of 3. Okay, so how many numbers is that? 2017 divided by 3 is, so 600 gives us 1800 when times by 3. 70 times 3 is 210, so that gives us 2010, so we're left with a 2 and a 1/3. Okay, so we've crossed out 672 numbers. Next, she reinstated all those integers that are multiples of 6. Okay, so essentially she brings back half of them. So let's just check that. So 2017 divided by 6 should be half of this, so 336 and 1/6. So she reinstates these. So she's minus 672 numbers, and she's added back in 336 numbers. And what we're essentially left with is we're left with all the numbers that aren't multiples of 3, like 1 and 2, and 4 and 5, and 7 and 8, and 10 and 11, etc. And then we've taken all of the multiples of 3 off and then only reinstated the multiples of 6. So we've got 6 and we've got 12, but we don't have 3 or 9 or 15, etc. Now she erases all the integers that are a multiple of 27. Okay, so we're still only interested in multiples of 3, but the thing to be careful of is the multiples of 3 which aren't multiples of 6 are no longer there. So we haven't got, in terms of multiples of 3, we've only got 6, 12, 18, 24. Notice that we skip 27, but we do have 54 because that's a multiple of 6. So actually, when we now erase the multiples of 27, what we're actually doing is erasing the multiples of 54. How many numbers is that? Well, 2017 divided by 54, well, it's going to be a bit less than 40, so 30 gives us 1500 plus 120. So, okay, 36 times 54, that's not quite big enough. Let's try 37. 37 times 54, you have to do these calculations sometimes, it feels a bit stupid, but back to primary school. 28 gives us 12 plus 35, that's 47, I think. 4, 15 plus 4, 1978. No, that's not right, is it? I think it's 1998. And then we add on another 19. So, anyway, essentially, we erase another 37. So in total what we've done is we started with 2017, we minused, so how many have we erased? We erased 672, but then we reinstated 336, but then we erased a further 37. And we know that that is half that, so that's just 336 plus 37, which is 373. That's how many numbers we erased. Okay, nice. Question 7. 3 rectangles are placed mutually adjacent, like this, without gaps or overlaps to form a larger rectangle. Okay, so it needs to be like that. One of these, okay, so one rectangle has 70 by 110, 110. Another rectangle has dimensions 40 by 80. What is the maximum perimeter? So it looks like we've got a few different cases. We've got, well, let's say it was like this. That's a bad drawing. Let's say it was like this. Okay, let's draw it again. We've got our rectangle, 70 by 110. And we could add a 40 by 80 like this. Yeah, that's more like it. 40 by 80. And that forces the third one to be like this. So case 1, the perimeter is, well, we've got 190 by 70. And so actually the perimeter is 380 plus 140 because we've got 2 of these and 2 of these. And that gives us 520. So that's case 1. What about case 2? How else could we configure these 3 rectangles? Well, a simple way of doing it would just be to reverse how we had that box. So like this. So now we've got 40 by 80, and that forces this to come up like this. And in case 2, the perimeter, it looks like it's going to be smaller, so it's going to be 160 plus, that's 2 lots of this, plus 2 lots of 150, which is 300. So the perimeter here would be 460. Okay, but can we do any better? Let's try again. Another option is if we choose the short side to add it to. So we could have it like this, 80 by 40, and that would give us this rectangle. So case 3 would be, well, this length is 150, so we get 300 plus 2 lots of this, that's plus 220, so that gives us 520. So well, that's actually the same as case 3. Finally, we have the option of using the same side but going up like this. So that's 40 and 80, and that completes into a rectangle like this. And the perimeter here in case 4 is 2 lots of this, that's 220, plus 2 lots of this, so that's 220 again, that gives us 440. So the maximum possible maximum perimeter of the third rectangle. Oh, I misread the question. Okay, that happens. So in case 4, the fourth rectangle is this little thing. So it's 40 by 30. So we've got 40, 80 plus 60. Case 4, the perimeter of the third rectangle is, in fact, 140. In case 3, we had it the other way around. So it was 80 by 40. Oh, that's so sad. So actually what we had was an 80 by 70. So that's going to give us 160 plus 140, which is 300. So in here we had P3 is 300. That looks like it's probably going to be the biggest one. But let's just check our previous 2 cases. read the question, that's the moral of the story. So the other options were, we had 80 by 40, which gave us this thing, which would be 80 by 30, 160 plus 60, that's not going to be as big as 300. And the other case was, we have 40 by 80, which gave us this slim thing, but the perimeter of that is 110 by 10, so that's 220 plus 20. So I think the biggest maximum possible perimeter for the third rectangle is 300. I botched that, I will admit, but that's part of the process. When you make mistakes, you recover from them and you just plow on. So question 8. Preeti is learning a new language called Tedio. Sounds tedious. During her 1 hour lesson, which started at midday, she looks at the clock. And I always used to wonder about this as a kid. She notices that the hour hand and the minute hand make the same angle. How many whole seconds remain until the end of the lesson? So, what's the easiest way of doing this? So obviously, in an hour, the minute hand does that, 360 degrees, whereas the hour hand does this, 1/12 of 360 degrees, so it only rotates through 30 degrees. So let's make a function. So I'm going to say, okay, after t seconds, this is a t, after t seconds, how many angles has the hour hand rotated through? And, well, in 1 hour, it does 30 degrees. 1 hour is 3,600 seconds. So the answer is, after t seconds, it's going to have done 30 times t over 3,600. Or another way of writing that is t over 120. Meanwhile, the minute hand, it does 360 degrees of rotation in an hour. So actually, that rotates through t over 10 degrees. So, and we know that at this magical time t, which we're trying to find, this angle equals this angle. The x isn't so important, but the point is that h of t at this time t equals 360 minus m of t, because these angles add up. So we're really looking at this angle and this angle. Add up to 360. So that gives us, if we just plug in our expressions, that gives us that capital T over 120 equals 360 minus capital T over 10. And that gives us in turn that 360 is equal to, common denominator, I think that gives us 13t over 120. And that gives us that t is equal to 120 times 360 over 13. So that is 36 times 12 is 360 plus 72. So that's 432. And we add on the zeros, divide by 13. And that gives us 3,300. You could do this by long division, but I'm just 33. So 3 times 13. We're left with 2, and I think. Oh, so last digit must be. So that is going to be a 9. So I think that gives us 3,323 seconds with a remainder of 1. So how many seconds are left until the end of the lesson? Well, the lesson is an hour long, and we've already elapsed this many seconds. How many seconds are left? How many whole seconds remain? So this isn't a whole second, so what we're actually left with is this many seconds, and that is 276. Okay, question 9. Robin shoots 3 arrows at a target. He earns points for each shot. If any of his arrows miss the target, or if any 2 arrows hit adjacent regions, so if we hit one here, and then we hit one here, 0 points. Or even here, 0 points. Or even here, 0 points. Or even here, 0 points. Okay. how many different scores can he obtain? So if we do hit 1 out of 7, that rules out everything apart from 3. So isn't his score just 0? Because there are no... oh no, okay, so I think... okay, so the idea is he could just hit like 7, 7, 7. Or 11, 11, 11. Okay, so... okay, so he could... what are his possible... he could just hit 0. Plenty of ways of doing that. He could hit... so that would be, you know... he could hit 1, 1, 1, so he could get 3 points, or 15 points, or 21 points, or 9 points, or 27 points, or 31 points, 33 points, sorry. So that's all of the possible options when he hits all 3 the same, or if he gets 0. What remains to be considered is what happens when he hits 2, like let's say 2 7s. Where could his third shot go? Well, we've already considered where it goes in an adjacent region, that would give him 0, or in the same region, which would give him 21, which we've already recorded. So what remains is, where are the non-adjacent regions? And the answer is just 3. So he could hit 2 7s and a 3, which would give him 17 points. But now we need to look at the other cases. So he could hit 2 3s and a 7, so that would be 13 points. He could hit 2 1s and a 5, which would be 7 points. He could hit 2 5s and a 1, which would be 11 points. He could hit 2 9s and an 11, which would be 29, I think. He could hit 2 11s and a 9, which would give him 31. And are there any other possibilities? 5, 6, 7, 8, 9, 10, 11, 12, 13. I don't think there are any other possibilities. So I think the answer is that there are 13 different scores. Okay, question 10. At each of the vertices of a cube sits a munchkin. Okay, so adjacent means they have to be linked by an edge like this. And they either always tell the truth or always lie. All 8 of them say, I am adjacent to 2 liars. What is the maximum number of munchkins who are telling the truth? Well, there's lots of symmetry here, so let's just say, let's say 1 stands for truth and 0 stands for lie. So let's say this is telling the truth, because we're trying to find the maximum number. If he's telling the truth and he's saying I'm adjacent to 2 liars, exactly 2 liars, that means, well, we've got lots of symmetry, so we can just say these 2 are liars and this is telling the truth. Now, if this one is lying and it's saying I'm adjacent to exactly 2 liars, then, well, it can't be the case that these are both 0, because that would mean this is telling the truth, and we know that it's not, it's lying. So one of these, at least, must be a 1. But this one is telling the truth, and so actually this one must be adjacent to 2 liars, which means this one must be telling the truth. And what we're left with now is, well, this one is adjacent to exactly 2 liars, this one and this one, so this must be also telling the truth. So the maximum number of munchkins telling the truth is 4. Okay, so question 11. An infinite arithmetic progression of positive integers. So that just means something like 2, 4, 6, 8. That's an infinite arithmetic progression. Contains the terms 7, 11, 15, 71, 75, 79. The first term in the progression is 7. So what we notice, is actually all of these numbers, 7, 11, 15, 71, 75, 79, they are all 3 mod 4. So all that means is they are a multiple of 4 minus 1. So if we add 1 to these numbers, we get 8, 12, 16, 72, 76, and 70. Sorry, that should be 79. And so adding 1 to it, we get 80. These are all multiples of 4. And so that means that this arithmetic progression has to either increase by 1s, or by 2s, or by 4s. So we've got 3 cases. If it increases by 1 and starts with 7, it's going to go like this: 7, 8, 9, 10, etc. And so the nth term, if we say this is the first term, this is the second term, this is the third term, the nth term, an, is simply given by, I think it's just 6 plus n. And we're looking for the possible values for the 100th term. So the 100th term is 106. Okay, brilliant. So what if it goes plus 2? What if it goes 7, 9, 11, 13? Well, the nth term in that case is going to be, well, they're increasing by 2n, and I think it's going to be 5 plus 2n. So the 100th term, if we plug in n equals 100, is 205. And if it increases by 4, like this, 7, 11, 15, 19, then the nth term is going to be 4 plus 4n. Is it? No, it's going to be 3 plus 4n. And so the 100th term is going to be 403. What is the sum of all of the possible values for the 100th term? Well, the sum is simply 106 plus 205 plus 403. And if we add that all up, we get 714, I think. Okay, so that's the answer. Question 12. The pattern shown in the diagram is constructed using semicircles, and the distance between here is 1 black dot. What is the area of the pattern shaded in grey? Okay, let's just zoom in here if we can. So let's look at the area of the grey. So we can consider this. Right, so the radius, so this is half a centimetre, or no, 1 centimetre. So the radius of this little one is half a centimetre. And we're looking at semicircles, so the formula is half pi r squared, but we're considering the radius to be half a centimetre. So actually, if we scale up, the reason I think it's got this 8 here is because we can take out 3 factors of 2. So that's 1 because the radius is a half, is 1 because it's a semicircle, and then 2 factors of 2 because the radius is a half, and we're doing half squared. And now we can consider the idea that this is 1 centimetre, because we've taken out a factor of 4 for that. And we got 1/8, and then we get the area of this. So now we can just write pi, well, let's take out a pi as well. Then we've just got 1 squared, so that's this. And then we've got this thing, the grey, but that's just plus, we're saying that this has now got a radius of 3/2. We've taken out a factor of 4, so we've got 3 squared minus this bit, which is just 1 squared. And now we've got to consider this, but that's just this semicircle, take away this semicircle. So that's plus 5 squared minus 3 squared, and we just keep on going. All the way to, well, this is 1, 2, 3, 4, 5.5. So we go plus 9 squared minus 7 squared plus 11 squared minus 9 squared. And so we've got basically all of these cancel. 5 cancels, 7 cancels, 9 cancels, so we're just left with 11 squared, and so k is 11 squared, which is 121. Question 13. In this expression, letters stand for different non-zero digits, but the same letter always stands for the same digit. What is the smallest possible integer value of the expression? Okay, well, we can do some cancellation. So we're left with Kangaroo over me. We're looking for the smallest possible integer value, so we want to minimize this and maximize this. Well, that's pretty easy. To minimize this, we need to minimize this because it occurs twice. So we can say that O is 1, so we get 1 squared times, and then we can just assign the smallest left values. So we get this 1 squared times 2 times 3 times 4 times 5. Over to maximize this, we're going to say 9 times 8. Now, I recognize the top as just being 5 factorial, which I know is 120, and the bottom is 72. And so this is well, it's between 1 and 2. I think it's actually 1 and 2/3. So my claim then is, we know it has to be bigger than this, but my claim is that we can find an integer value of 2. Now I just have to find it. So let's keep the bottom the same. Now that's 72. And so we need the top to be 144 for it to cancel down to 2. And we could get that by doing 1 squared times, well, 2 times 3 times 4. That gives us 4 factorial, which is 24. Now to make that 144, we could just times by 6 to get 144. So actually this is realized. We do have integers, different non-zero integers, putting it into here so that we get an answer of 2. So my answer is the smallest integer value it can take is 2. Okay, let's do question 14. This set with the numbers 1 to 6 has, we've got some non-empty subsets. So t, for example, could be 1, 4, something like that. It just means you take some of the numbers, you don't take none of the numbers. And these subsets have the property that it contains no pairs of integers that share a common factor other than 1. Okay, so all of the numbers in T are coprime. So, for example, we could have 1, 4, but we couldn't have 2, 4 because they share a factor of 2. How many distinct possibilities are there for T? Okay, so this is going to be a listing exercise, I think. Well, we could have just one element in T, so we could just have 1 or 2 or 3 or 4 or 5 or 6. What if we had 2 elements in T? So we could just, well, one is, we could have 1 and any of these elements because they can't share a common factor other than 1, but they can share the common factor of 1. So we could have 1, 2, or 1, 3, or 1, 4, or 1, 5, or 1, 6. But we could also have a pair of elements like 2 and 3, which are coprime. So we could have 2, 3, we could have 2, 5, we could have 3, 4, we could have 3, 5, we could have 5, 6. And I think that's everything. We could also have 3 elements. Oh, hang on. We could have 4, 5. Yeah. And then we could have 3 elements in the set. So we could have 1, 2, 3, or 1, 2, 5. We could also have 1, 3, 4, or 1, 3, 5. We could have 1, 5, 6. So that's just mimicking all of these, and 1, 4, 5. That's just all of these, but with an extra 1 in. But we could also have the ones where we've just got 3 coprime elements, like 2, 3, 5, and 3, 4, 5. I think that's all, because 6 has a factor of 2 and 3, so we can't have any 6s. And we could have T with 4 elements in, but it would have to be either 1, 2, 3, 5, or 1, 3, 4, 5. And we can't have any subsets with 5 or 6 elements in, because one of them would have to be not coprime to one of the others. So in total we've got 6 plus, how many have we got of size 2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, plus 11, plus 1, 2, 3, 4, 5, 6, 7, 8, so we've got plus 8, plus 2, and when we add them all together we get a total of 27, so this is our answer. Okay, question 15. Ugh, I don't like these sorts of questions. Okay. Okay, let's just get stuck in. 1 across has to be a 2-digit square, so it has to be one of these. What have we got? 64, 81, and that's okay. 3 across, that's the answer to the kangaroo question, so we'll have to find that last. 1 down, 4 down. 1 down is 4 down minus 11, so that's useless. But 2 down is 1 less than a cube, and it is 3 digits. Okay, the 3-digit cubes are, well, 5 cubed is 125, So we've got 124. 6 cubed is 216, I think, so 215. 7 cubed is 343, so 342. 8 cubed is 2 to the 9, which is 512, so we've got 511. 9 cubed, I think, is 729. This would really be difficult if you didn't know your squares and cubes. And then 10 cubed is 1000, so we can't have that. Oh no, we can, because we're minusing 1. So we've got 728 and we've got 999. And so the 2-digit ones go here and the 3-digit ones go here. So if we look at the last digit here, that has to be the first digit here. So the only options are, well, there are actually a few options. We could have 25 here, and say 25 here, and 511 like this. Okay, let's look at that. So that's going to mean, what's that going to mean? That's basically going to mean that, okay, well 5 has to be a square, so this has to be 16. And that's going to mean, if we look at this, 4 down minus 11 is 1 down. So that's going to mean if we minus 11, we're going to get 5 as the last digit, and then that's just going to mean we're going to get this. So that could be right, I think. Does that contradict anything? The highest common factor of 1 down and 4 down is greater than 1. That's not true. 25 is 5 squared, 36 is 6 squared. Okay, so that is not a possibility. What else could we have? We could have 49 here and 999 here. So what does that give us? Oh, well, there's no square, there's no 2-digit square that begins with a 9, so that can't be true. What else do we have? I might have gone wrong here. We could have 81 and, well, 124. So we could have 81 and 124. Now that implies that there must be a 9 here. And now we need this minus 11 to be this. So, and we also need the highest common factor of 1 down and 4 down to be greater than 1. How do we do that? 8. 4 down minus 11. Okay, so this has to be an 8 because we're minusing 11 from a number that ends with a 9. And then adding 11 back, that gives us 99. And these do share a factor of 11. Okay, good. So I think that means we're done. And the answer to the kangaroo question is 3 across, which is 8 to 9. Brilliant. Question 16. So the curve x squared plus y squared is 25 is drawn. That's just a circle with radius 5. Points on the curve whose x coordinate and y coordinate are both integers are marked with crosses. Okay, so the idea here is basically to remember our Pythagorean triplets. So we've got these integers, obviously, integer points, but we've also got these ones. This is like 3, 4, 4, 3, and then we've got the same but with minuses here. And then we make a polygon like this, and we need to find the area of the polygon. Oh, I like this question. So if I can rub this away, hopefully you saw the symmetry there. There's a lot of symmetry. We only really need to consider the upper quartile of our graph, the upper quadrant, sorry. So we've got 5, 0 here. We've got 0, sorry, no we haven't. We've got 0, 5 here. There we go, 0, 5 here, and we've got 5, 0 here. And we've got 3, 4, 3, 4, and we've got 4, 3, and these are all connected like this. Now, I think what I'm going to do is, because we know that all of these points straight away, we know that these lines that I've just drawn all have length 5, I think I'm going to find the area of this, find the area and then times it by 2 to get the area of these two, find the area of this, and then we'll just times it all by 4 to get the area of P. So first we've got this triangle. Now it's isosceles because we've got a 5 and a 5. So I can actually split it in half like this. And if we look at the distance between 0, 5 and 3, 4, we see by Pythagoras that's going to be 0 to 3 is a jump of 3 squared, so it's going to be 3 squared, plus 5 to 4 is a jump of 1 squared, so it's actually going to be root 10. So the area of this bit is going to be root 10 over 2. And similarly, if we split this triangle in half, this distance is going to be root 2 over 2 because of the distance between these 2 points. So the area of P is, we've got 8 of these ones, so we've got 8 times the area of this triangle, which looks like this. We've got a base of root 10 over 2 and we've got a hypotenuse of 5. Plus, we've got 4 of these, which is 4 times the area of this triangle, which has a base of root 2 over 2 and a hypotenuse of 5. Okay, well let's just work them out up here. So let's call this x and this y. We've got by Pythagoras x squared plus root 10 over 2 squared is 10 over 4 equals 5 squared, which is 25, which means that x squared, common denominator, is 90 over 4, and so x is square rooting that 3 root 10 over 2. Similarly, y squared by Pythagoras plus root 2 over 2 squared, which is a half, equals 5 squared, which is 25. So we get y squared, common denominator, is 49 over 2, which means y is 7 over root 2, which is 7 root 2 over 2. So we now get the perimeter is 8 times, let's see, we've got half times base times height, which is x, which we found was 3 root 10 over 2, plus 4 times a half times base times height, which is y, which is 7 root 2 over 2. Now let's work this all out. We've got a half, and a half, so we get 1 times root 10 times 3 root 10, which is 30 times 8, plus, no sorry, it's just 30, because this, and this cancel with the 8. And then we've got, sorry if I just wrote those out, and then we've got 4 times a half times a half times a half, which is a half times root 2 times root 2 is 2, so we just get 7 times hang on, what have I done? Half times, oh sorry, and these need to times by 2. So we've actually got, because this is only half of that triangle, so we've actually got 16 times that and 8 times that. 8 times that. So that's 16. So we've actually got 60 plus 14. And 60 times 14, 60 plus 14 rather, is 74. And that is our final answer. Okay, on to question 17. Matthew writes a list of all 3-digit squares backwards. Oh, okay, what are our 3-digit squares? So then he writes them backwards, and then discovers some of them are prime. And then what is the mean of those primes? Okay, this is going to be a computational one, I think. So let's write out our 3-digit squares. I don't see any other way of doing it. So 14 squared, 15 squared, 16 squared, 17 squared, 18 squared, 19 squared, 20 squared, 21 squared, 22 squared. All I'm doing at the moment, add 21, add 23, add 25, add 27. So, although I did know most of them up until this point, now I need to add 51, which is that, add 3, add 55, add 57, add 59, and add 61. Okay, these are our 3-digit squares. Those are, okay. Now we reverse them, so 65 to 526, and some of them are prime. Well, anything that starts with a 2 or a 4 or a 5 or a 6 or an 8, when we reverse it, the last digit is going to be one of these, and so it's definitely not going to be prime. So we can rule out this, and 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 this. Quite a lot of them actually. We can rule out those. Furthermore, any number whose digits add up to a multiple of 3 is itself a multiple of 3, and that property is not affected when we reverse the digits. So, which of these add up to a multiple of 3? This one does. 6 plus 9 is 15 to 16, no. This one 15 to 16, no. This one is 9. Okay, that's not going to be a prime upon reversal. This one, no. This one, yes, multiple of 3. No, this one's a multiple of 3, evidently. And 961, no. Okay, so we're left with a few numbers. Well, when we reverse this, I mean, this isn't prime, is it? Also, this is actually a square upon reversal. So are these. So we're left with these 3 numbers, and I don't see any reason why. Okay, so what are we actually left with? 691, 487, and 163. Now I see no reason for those not to be prime in the context of the question, so all we need to do is find their mean. So that's 691 plus 487 over 163 over 3, and that is going to give us, well, what's the numerator? 13, we got 1300 plus 9, so 1723, 2 plus 230 plus 11 over 3, which is 1541 over 3, and that is going to be 400 and 447. Yep, 447. Okay, so our answer is 447. Nice. Great, question 18. We're not going to quite finish this in under an hour, which is unfortunate, but we got pretty close, which is nice. So these questions might be a bit harder now. Okay, let's zoom in a bit. The diagram shows a semicircle. Okay, so the area of the... Okay, the semicircle has radius 10. So let's call this the origin of that circle. This is 10, this is 10. We're also told that CBA is 60 degrees. And the area of the rhombus is A root B, which is a proper third. Okay, okay, so the idea I think should be if we draw some lines, some helpful lines, just splitting the rhombus into 4. If we can find the area of the semicircle, that's quite easy. The area of the rhombus, if we can find the area of just this triangle, let's just call that Z or something. If we can find the area of this triangle, will be done, basically. So let's make that our aim. So we need to find the length of this, which is half the length of AC. And okay, so what do we know? We know that this is 60 degrees, so actually this is 30 degrees because of alternate corresponding angles. So, well, that's helpful. So actually this length here is going to be 10 tan 30. Now tan 30 is 1 over root 3, so that's 10 over root 3. Now, what else have we got? Okay, so if we actually want to know well, yeah, we can find AC now. No, we can't. We can find a... Yeah, we can find... Getting confused now. Okay, OC is 10 over root 3. But if we look at yeah, so if we try and find AO here, that's giving us AO is actually going to be 10 over sine 60, and sine 60 is root 3 over 2, so that's 20 over root 3. Okay, and now obviously AC, so wait, this is, what was this, OC, and this is AO. AC is AO plus OC, so AC is 30 over root 3, and we could write that as 10 root 3. 10 root 10 root 3. Okay, that's good. So what does that mean? Well, AZ is half of that, which is 5 root 3. So this is 5 root 3. Okay. 5 root 3. Ah, yeah, okay. And that is, and we know that this is 30 degrees. So now looking at the area of BZA, if we draw BZA, we've got BZA, AZ is 5 root 3, and this is 30 degrees. And so we can just write, well, essentially, we know then that it's half times 5 root 3 times this base, but this base is going to be, if you think about, we've got a tan of 30, and we know that tan of 30 is 1 over root 3, so this is actually going to be 5 root 3 times root 3, so that's 5 times 3, which is 15, and if we work that out, that's 75 root 3 over 2, and so actually the area of the rhombus is 4 times that, which is 150 root 3, and therefore, from our formula, that's A root B, and so we've got A is 150 and B is 3. Okay, so now we're trying to find AB plus A plus B, so that's 450 plus 153. So that is 603, final answer. Ooh, okay. Where's the next question? Question 19. Nearly done. Okay, so if we were doing this for real, I would have ran out of time basically here. Okay, so I would have only answered 18 of 20 questions. But that would have been more than enough, providing, assuming that most of these are correct, to get the merit. But we will, for the sake of completeness, just carry on and try and do questions 19 and 20, even if we go 5 or 10 minutes over time. So we've got a function, f of 1 of x is x, f of n plus 1 of x is 1 over 1 minus fn of x. Wow, and the integer c is a 3-digit cube such that the cth iteration of this function equals c when you plug c in. What is the largest possible value of c? Ugh. Okay. The only way this is really solvable, because look, this c is a 3-digit cube, so we are iterating this function hundreds of times. So the only way that's possible is if there's some kind of simple expression for fn of x. So f1 of x is x, so f2 of x is going to be 1 over 1 minus x. f3 of x is going to be basically 1 minus 1 and then 1 minus 1 of x. This needs to simplify, otherwise we're going to get very stuck. So 1, so common denominator 1 minus x minus 1, so we've got minus x over 1 minus x. and so we get, well, we get 1 minus x over minus x. How else can we write that? Well, that's x minus 1 over x, and we could write that as 1 minus 1 over x. So then what would f4 of x be? It would be 1, no it wouldn't, it would be just using this, so 1 over 1 minus this, so 1 minus 1 over x in brackets. Okay, so this is 1 over, these cancel, 1 over x. Okay, so f of 4 of x is x. So that essentially gives us, because this iterated, because remember f1 of x is x, and now we found f4 of x is x. So that means f7 of x will be x, etc. So actually we get that essentially f of 3k plus 1 is x. So for all k, for all integer k. Oh, sorry, that's of x equals x. So essentially what we're looking for is a 3-digit cube. Okay, we're looking for a 3-digit cube of the form 3k plus 1. What are the 3-digit cubes? Well, we've got 5 cubed, 6 cubed, 7 cubed, I hope this is right, 8 cubed, and 9 cubed. Which of these is of the form 3k plus 1? Well, it can't be 6 cubed, and it can't be 9 cubed, because they're multiples of 3 to start with. No, 123 is a multiple of 3, so it can't be that one. I think this is a multiple of 3 plus 1. And this one is oh wait, 3, 1, 1. No, 510 is a multiple of 3, so this isn't either. So it must be 343. Let's just check that. So that's 3 lots of 114 plus 1, I think. Yes, yes. So that is of the required form, so the answer is 343. And finally, we've got question 20. Let a, b, and c be positive integers such that this holds. What is the minimum possible number of factors of abc, including 1 and abc? Come on, we can do this. Okay, so this to me looks a little bit like the proof of the irrationality of root 2, where essentially, so a, okay, I'm not going to write all this, but please try and follow along. So a squared equals 2b cubed. 2b cubed is even, which means a squared must be even. But if a squared is even, then a is even. But if a is even, a squared is a multiple of 4. I'll just write that a even. A squared is a multiple of 4, which means b cubed is a multiple of 2. But that means b is a multiple of 2, so b is even. We can apply a very similar argument looking at this to show that c is even. And now let's consider this. Okay, so this is a multiple of 3, which means this is a multiple of 3. But that means that b cubed is a multiple of 3. But that means that b is a multiple of 3. So b multiple of 3. But that means that 2b cubed is a multiple of 27, which means this is a multiple of 27, which means this is a multiple of 9, which means c is a multiple of 3. And we can also do the same thing with this to show that a is a multiple of 3 because this is. So we get a is a multiple of 3 and we get that c is a multiple of 3. So immediately from these equations we know that a, b and c are all multiples, all have 2 and 3 in their prime factorizations with a non-zero power. But if we're looking for the minimum possible number of factors, then we don't need to add superfluous 5s and 7s, etc. into the prime factorization. So we can just say that a is 2 to the, I'm going to say x1, 3 to the y1, b is 2 to the x2, 3 to the y2, and C is 2 to the x3, 3 to the y3. Okay, now let's see. Now let's actually use these equations. A squared equals 2b cubed. That means that we've got 2 to the 2x1, 3 to the 2y1 equals 2 to the, let's be careful here, 3x2 plus 1, because we've got b cubed times 2, 3 to the 3y2, and then that equals 2 to the 5x3, 3 to the 5y3 plus 1. Okay, so all of these are equal. So that means we've got 2x1 equals 3x2 plus 1 equals 5x3, and so that's equation 1, and equation 2 is 2y1 equals 3y2 equals 5y3 plus 1. And remember, we're trying to find the minimum possible number of factors, so we're trying to minimize all of these. And these are going to be minimized, if we think about it, when x1 is, well, x1 is going to be 5 to make, because, well, 2x1 equals 5, y3. x3 is going to be 2. Does that work? Well, 3 lots of 3 plus 1 is 10, so x2 is going to be 3. So that works. And that's going to be the smallest values for the x's. For the y's, similarly, we've got 5y3 plus 1. So let's try y1 is 3, y2 is 2, and y3 is 1. That makes all of these equal to 6. So they're the smallest. So actually we found that A equals 2 to the 5, 3 to the 3. We found that B is 2 to the 3, 3 to the 2. And we found that C is 2 to the 3, 3 to the 1. So ABC, timesing all these together, is 2 to the 5 plus 3 plus 3, which is 11, and 3 to the 3 plus 2 plus 1, which is 6. How many factors does that have? Well, in any factor is going to be 2 to the, let's say, 2 to the j, 3 to the k. J could be 0 all the way up to 11, and k could be 0 all the way up to 6. And each of these different choices of j and k is going to lead to a different factor of ABC, including ABC and 1, because of uniqueness of prime factorization. So actually we have 12 elements here. 5. Sorry, I've done, one of these should be a, I think C is a 2, sorry, that should be a 2 there, so that should be a 10 there, so that should be a 10 there. So if we look at the number of elements in each of these sets, we've got 11 elements in here, possibilities for the power of 2, and we've got 7 possibilities here, so the number of factors of ABC is actually going to be 77, so our answer is going to be 077. Okay, so we're done. I think we took about 1 hour and 10 minutes to do all of those, but I think we did actually do all 20. So hopefully that was a helpful walkthrough of the solutions, and also I hope that helped you to see the thought process that I went through. Sometimes I kind of saw what to do quite quickly, other times I didn't really know what to do, so I just had to go out on a limb and give it a go. But yeah, these are difficult questions for 6th form and year 11 to do, so well done if you got a few of these. But yeah, so there you go. That's how to give the Senior Kangaroo Math Challenge a go, and for all of you who are taking this exam in the near future, I wish you the very best of luck, and I hope you go on to enjoy maths for the rest of your life. But that's this video done. Hope you enjoyed it. See you soon.